All right, and hello everybody, and welcome. I'm glad you're here. I am continuing my discussion about the idea of hydraulic cylinders to create a human mimicking robot. And I'm always on the lookout for examples, and it struck me it would be like they had looked at tennis and they wanted to do a tennis mimicking new set of equipment. But they had systems in place and had looked at that flexible plastic and the fiber material and the polymers with the good modulus of elasticity and compressive and reactive strength, where you can have a tennis ball that hits the ground and bounces. And they thought those chemicals just smelled bad and they were hard to work with and a little bit dangerous. And they didn't have the equipment for doing that. So they were going to make this new version of tennis using a tennis ball system that they were happy with. And what they had decided to do was make a tennis ball out of seasoned white oak in a sphere. Well, they had made a sphere the size of a tennis ball, but the equipment kept breaking it, and they didn't want to buy new equipment. So instead, they're going to have a tennis ball made of seasoned white oak, and it's the same size as a softball. And they, of course, needed to make a racket out of alloy stainless steel with steel netting, because anything else that hit that ball, it would just destroy. That doesn't look like tennis to me. And they're like, well, we have an education in sports medicine and sports physiology, and we have the ability to declare what is tennis, and you don't. And I keep thinking, yeah, but it doesn't look like tennis. That's not how tennis works. And the same, I think, is true with the non-hydraulic cylinder human mimicking robots. You can see that I have these hydraulic cylinders in here powering the joints. And they have the force and strength and speed of motion and ability to move this robot around like a human being. And the simple truth of electric motor gearhead systems is you can't get an electric motor gearhead system of this size that has enough strength to run this foot. It just won't work. But I wanted to explore how this could all be put together and you could make a robot, and that's what I'm doing. Now, I'm pretty sure I'm going to need to add a physically real set of structures to prove this, and I need to get them built. And the CNC people want the particular high quality drawing programs that they want. One of them is Autodesk Fusion, and so I don't mind Autodesk Fusion. I just have to learn how to use it. I've done a little bit of it. I did create a cross section that was constrained. That having it constrained seems very important to Fusion. I have not yet seen why it's important. And I did take a cross section and revolve it to get a solid. I can show you that. So I'm getting there with Fusion, but I'm not there yet. So I do have in Fusion, there is the square cross section O-ring, and there's the Delrin, and here's the cross section of that structure. And here is a revolve that I did with it to a solid structure. So I'm getting there. I don't fully understand Fusion yet, but I'm getting there. But we're going to talk a little bit about the robot walking. And part of the robot walking is this taking of steps as it steps along. And this is not, in order to show this, it's not quite what you think. This is what it really looks like. But I spaced them all out so you can see how the robot is walking. And of course, I always want to add hello and welcome and take a look at where we are. This is my computer screen. The actual, this is what is being shown, She Beach, which seems a little gloomy to me. It's pretty. And I thought I would go back to England. That's kind of pretty. That's quite a house. Just imagine the heating bill. All right, and we'll get back into the computer. And the other thing I like to mention in these lectures, I always like to make sure, let everybody know that I'm glad you're here and welcome. I do have a website, Pistonrobot. Hydraulic walking is one of my topic areas. I'm not sure if I might do something about how the robot walks. I might make that a separate page. But the other thing is, this is a physically real structure if it was created, and it's hydraulic. And any physically real structure has the potential to hurt somebody. And if you're going to work with a physically real structure, my advice is to manage it in a manner that is legally allowed and reasonable and safe. And if you can't do that, then my advice is do not create it as a physically real structure. And we'll go back to where we were. All right, and we're back where we were in the drawings. Now, this was a human mimicking robot. And what's interesting is if you're going to mimic a human, there's a lot of measurements that are already there that you don't need to make. They just come because it's a mimic of a human. It's 6 feet tall. The pelvis is about halfway up. The knee is about halfway up the leg. The stride is about this distance. All of these numbers are already constrained and exist. And so there's measurements you can make, but you don't have to come up with an answer for every single thing because it's already there since you're mimicking a human. The robot has the joints, the ankle joint has 2 ranges of motion, dorsiflexion, plantarflexion, eversion, inversion. The knee has only one axis of motion, flexion, extension. The hip has 3 axes of motion, internal, external rotation, abduction, adduction, etc. And these ranges of motion, this robot is physically constructed so that these joints are the joints of a human being and they have the range of motion that a human being has. And we need to discuss the convention with which human beings walk. They walk in a certain way. They have 2 feet. And one foot has one designation and the other foot has a different designation. There's the foot that's on the ground, holding up the weight of the robot. It's Atlas with the world on his shoulders. One foot is holding up the weight of the robot. The other foot becomes Freebird. It can move. It's not holding up anything. And it actually is very close to having the behavior of an airplane in that it begins like, see, you can see here's the right foot down and it's getting ready to be the foot in the air. So it does a pre-flight evaluation where it makes sure that the other foot is holding up the weight and it gets itself ready and goes up in the air and it flies along through the air and then comes back down and lands and becomes the foot that's on the ground. So the foot that was not on the ground becomes the foot that was on the ground, and the foot that was released and allowed to fly is the foot that's moved forward. And that's the way the robot walks, is because it can move one of its feet forward. And it manages its weight in a way where when this free foot is moving forward, the stability and balance of the robot is adjusted so that even though this leg is moving around and swinging, the behavior of the robot with respect to the foot on the ground is of a type that keeps the robot balanced. It can tilt a little bit, but it doesn't tilt enough to fall over. And all of this is the way that human beings walk, and it's already set. So you don't need to decide to do that, or you don't have much of an option of how you're going to do that, because I thought it made sense for the robot to walk along the way that people walk along. And these dimensions, this length of 1 foot moving forward is about 14 inches. And if you take the entire stride where the right foot is down and in the back, and it goes to the left foot is down and in the front, and the right foot is lifted up and brought forward and becomes the foot in the front, and then the left foot is picked up and swung forward, and at that point the right foot becomes the foot that's on the ground and in the back. And so the very next position of the robot after this one is this one, and it starts over again. It's a cycle. And this is robot position 3. That's because position 1, the robot's just standing there, balanced, doing nothing. Position 2 is halfway between 1 and 3. Position 3 is where it's actually doing the cycle of walking. And I split this into 22 separate poses because it seemed to me when it moved about that much, it was time to make a copy. And the distance that the robot travels with one cycle of walking is 38 inches. So what happens is those 22 cycles of movement need to be compressed into 38 inches. And that stacks the robots together, which is okay. You can make an image of each of these positions and render it and stitch it together as a movie, and you get a movie of the robot walking. And I did that and put that on my website. I've already shown you that movie. And so I'm trying to start way up high, and we'll work our way down to more and more detail. And this is a granularity-based concept of how the robot walks, in that we're not going to have a smooth and continuous motion. We're going to go from one position a little bit to the next position, and a little bit to the next position, and a little bit to the next position, so that we can state this and discuss it in a way where it can be comprehended. And she is standing on one leg and pointing at the clock, which is my secret message that I've used up my time. But that's okay. I'm going to do this in a series of 15-minute lectures. We're laying out the basics of how this robot is structured, and we will get into a lot more granularity, one section at a time. All right, and hello everybody, and welcome. We're continuing our discussion of the robot walking along on the concept of quantum thinking, where it moves from one stance to the next stance, like the valence electrons of chemicals and elements. They can go from one level to another level, but they don't go in between. And we're trying to put together stances because that allows us to make a definition of what's going on. And with walking, we have to have the robot walking in a straight line. That's important. But another feature of walking is the changing of your heading. So if you're headed due north, you can make a left turn of 90 degrees, and now you're walking due west. But you can also make a left turn, but it's not a left turn of 90 degrees, it's a left turn of 2 degrees west of north. And that's your new heading. So you can talk about, is it a left turn or a right turn, and you can talk about what are the number of degrees of turn that you put into it. And we've shown the robot walking along. This is the group of poses or stances for straight line walking and how they get pushed together for scale purposes. And I spread them out so you can see what they are. And you also have the walking of turns where the robot changes its heading from walking in one direction to walking in another direction. And we're going to go over a little bit more of that. And of course, like I said before, it's always kind of fun to see where we are. Let's see, this is the Bing background. Glacial rivers of Iceland. And I think many times people say, gee whiz, Dr. Gray, when you start explaining stuff, the phrase glacial comes up. But I want to go slow, get the details straight. We'll get ourselves back up into where we're supposed to be so that people understand what I'm talking about, because it's going to get a lot more detailed. And I don't want people saying, I just don't understand what's going on. I would rather that they know, and they're like, of course, and that goes to there, and that goes to there, and that goes to there. It all fits together. So that's what I'm doing. And this is a turn, and this is a expansion of that turn. Now, on the issue of walking, we've already done that the humans put a foot down. There's 2 feet conditions. One foot condition is holding up the weight of the robot, and the other foot condition is free. I'm free. I believe I can fly. And it's the free foot that can swing forward and allows the human being to move forward. If they didn't have the free foot to move forward, they wouldn't be able to do anything. And that's an issue, and we're going to do a little bit more detail of that. But let's take a look at one thing. And we'll be at this static scene, and I just wanted you to, let's go over to the website and see the movie that we're able to make using this method of walking. And we have the Pistonrobot. This is my image that I picked. This is just the robot kind of walking along. Hi. So we'll go to, I wanted to show you where this is. Discussions about a piston robot. Then piston robot discussions. This is the watcher that keeps up with the website to be sure everything's okay. This is this little video I made of the robot walking. You can download it to your own desktop if you want. And when we click on it to get to it and hit go, then it shows the robot walking along. Okay. And to me, looking at this, my feeling is this is the way human beings walk. And all the little electric motor gearhead robots, they don't walk like this. They have this mincing little careful, scared way of walking. They walk to me like the people I've seen that have acute appendicitis. And I think they're just being careful. They don't want anything to go wrong. And my robot's leaning left, leaning right, leaning forward, leaning back, picking its feet up, swinging them forward. This is the kind of walking that human beings do. And I think the kind of walking you can do with hydraulic cylinders. All right, so we'll hold on that for a second and go back to this. And remember, we had this walking style. There's the foot that's down holding up the weight of the robot and the foot that can move forward. And I think when human beings turn, Okay, they can turn left or turn right. I think they turn off of the foot that's in front. So you can have your left foot in front or your right foot in front. So we'll talk about a left turn with the left foot in front. I call that a left turn off of the left foot. Or you can have a left turn with the right foot out in front. And I call that a left turn off of the right foot. And then you have right turn. So you can have a right turn off of the right foot, a right turn off of the left foot. And this is normal, regular humans walking along, not ultra athletes or godlike special forces people or gymnastics experts that can do anything. That's not what I'm talking about. I'm talking about he got to the boardwalk with the girl that he thinks is so beautiful, and she's finally going to talk to him, and they've got ice cream cones. They're walking along. He's trying to get a sparkle in his eye. He's a guy. He has no idea how to get a sparkle in his eye, but he wants to impress her and talk about this and pay attention to whatever she's doing. And he's just walking. He's not paying any attention at all to how his legs and feet are working. And if he wants to turn, he makes a turn. If he wants to turn a little bit, he makes a turn a little bit. And that's the kind of turn I'm talking about. And I have here, I think, an example of a turn. And this looks like it's a left turn. And the robot planted its left foot. So this is a left turn off of the left foot. That's what we're showing here. I did want to bring out, when you were watching the robot walking on this is a specifically designed course. So straight line walking, here's one left turn, here's another left turn, here's a third left turn, back to straight line, right turn, right turn, right turn. So this, as you watch the movie on my website, there's a left turn off of the left foot somewhere in here, and the next one is a left turn off of the right foot, and then a left turn off of the left foot, and then a right turn off of the left foot, a right turn off of the right foot, a right turn off of the left foot. That's why this figure of 8 is put together the way that it is. And as you watch the real-time movie and you watch the robot turn, and you say, I'm not sure that's how that doesn't look right. I don't know, that's kind of not, it's kind of jerky and not what a human would do. But in my opinion, if you're doing that, you're already on my side, because that's the exact point I'm trying to make. When you have a human mimicking robot built just like a human with the joints, parts, power, strength, speed of a human being, you don't have any trouble figuring out how to get the robot to move. You just say, well, this is what I would do. And I'm like, okay, I don't mind that. And you might say, well, this left turn off of a left foot, he's kind of swinging his leg out there. I mean, what's that all about? And I would say, okay, you do it. Draw it so it's smooth like you like. In order to do this, I have to dial in and move each one of these little hydraulic cylinders, and then I have to move the parts so that everything lines up like it's supposed to. And I'm doing this, you really sort of have to have one that you're looking at and a mental picture of how this all fits together. But what I wanted you to see was, I think you can certainly, particularly if you have the strength, proportions, power, and speed and form factor to create a human, like that leg, that just doesn't look quite right, then you can create a human robot that walks along and doesn't do that weird way of walking that the other ones do, the electric motor gearhead robots. And I did want to go out to show how smooth and how well this works in the real situation. And of course, we're going to say, let's not have any snarky remarks about the model. We're glad that the model has agreed to do this. These are some left turns. I think there's going to be a left turn off of the left foot and a left turn off of the right foot. So let's see how this goes. We'll click here. The feet are moving. There's the right foot's been put down and the left turn has been made. So that is a left turn off of the right foot. We'll see if we can run it again. So it starts walking, plants the right foot, swings the left foot over, left turn off of the right foot. That's not bad in real time with real humans. Let's look at the other one. I'm going to say it's subtle. So here we go. The walking has started. We plant the left foot and swing the right foot around and swing it around again. And that is a left turn off of the left foot. One more time. The left foot is planted and the feet swing around, and that's the left turn off of the left foot. You can see how nice and smooth and easy this is with real structures. And again, we're not going to say anything about the model. He's a nice guy. He was a Navy diver. He agreed to do this. The robot has fallen down and has to get up. That's the final thing. We did straight line walking and turns, now getting up. And what happens is swinging the pelvis, lifting the pelvis off the ground, swinging the pelvis over and replacing it on the ground, and then swinging over the thorax, putting the arms down and generating basically a 4 support stable structure. And now we're going to create a 3 support structure that allows this foot to come up. Balance begins and the other foot is brought up, and the person, the robot, is up off the ground. And that took about 40 seconds. Smooth and easy. And she's lying on the ground on her back and has put the clock on her face. We're out of time. All right, well, I'll stop here and we'll start again with another one. All right, and hello everybody, welcome back. We are working on our concept of a human mimicking robot that walks along like a human being, and this issue of that it just seems like the electric motor gearhead robots that are out there, they don't walk like human beings walk. I'm not real sure. Well, I think I know why. I think there's an issue with the robot that I've talked about, which is if it's going to be a human mimicking robot, you have to kind of squeeze all the stuff into a human shaped form. And that includes your prime movers, the thing that move the parts of the robot. They can't be just arbitrarily big. And I think they've discovered that the electric motor gearhead systems, when they get small enough to fit and they add enough power to them to move a human-sized robot around, 6 feet tall, 200 pounds, if you put that much electrical power into something this small, it will burn it up. They can't do it. And so they just said, okay, fine. We'll just declare that a human mimicking robot doesn't have to walk like a human being. It's not necessary. And that solved the problem for them. And I'm back there saying, well, but if it's a human mimicking robot, why does it not mimic what a human being does? And they're like, well, you don't have a university education in robots, so you don't really, it doesn't matter that you have a question. All right, I'll get off of my soapbox and we'll do some other things. And the hypothesis I have is the concept of how are you going to tell this robot what to do exactly? And my thinking was to have a set of stances where 3A goes all the way up to 22A, and then the next thing that happens after 22A is 3A. And so the robot just goes through these stances, It's like those pianos where you have a roll of paper and you insert the roll in there, and it's a player piano. And as the roll of paper goes through, it plays the song. And I think that's a perfectly reasonable way to get a robot to walk along in a way where somebody's going to say, all right, here is this hydraulic cylinder right here. And the amount of extension of it is this many millimeters, okay? And if it's this many millimeters, hang on a second, and you're doing this stance concept, and it has been extended by this many millimeters, and we're measuring it to the 100th of a millimeter, and we're on stance 7, and we're getting ready to go to stance 8. And so this looks like you can see that this leg has swung back. And part of the way that it has swung back is that this amount of retraction has become this amount of retraction. And somebody's going to say, look, I will do this, but you have to tell us numerically what you want. And that's why I wanted to do it with stances, because we can go from stances along. And if we're at number 9, the next thing we're going to do is number 10. And so that was the thinking process. And as you know, I always like to take a peek at what we're up to. And this is my desktop from Bing. California sea lion in a forest of giant kelp. And my feeling is, first of all, this is a science discussion about me making something work based on how I thought about it. Translation, murky. Translation, we're really in an environment that's a little bit not our environment. But he's happy and he's in his element, and we'll just see what happens. So back to what's available here. And as I talk, I'm going to just show these stances. And it is walking. There is a chance it will become off balance. So because of, who knows, anything. This right here, when he went from 10 to 11, let's see, where he went from 7 here, where his foot's off the ground, to 8, where his left foot is on the ground, he stepped on a rock. And so stance 9 is not quite as stable as we thought, because something happened that we hadn't planned on. So it may be that stance 10 is going to have to be stance 10 as modified, because we have to do something because of the rock. On the other hand, if there's no rock and all is cool and it looks good and there's no balance or tilt over issues, if you're on stance 9, you just go to stance 10. That's the thinking process. And I wanted to have an understanding of things that you have to look at, some of which I think is non-intuitive. And in the world of human beings, I think the word non-intuitive means the first few times you thought about it, you had a good feeling for what's going on, but actually you were wrong. That's part 1. Part 2 of non-intuitive is when I explain it to you, or when someone explains it to you, the first few go-rounds, your reaction is, well, that's just not true. And that's what non-intuitive is. And we have to look at these stances and these legs and how we're going to put this robot together to be walking along where it doesn't fall down. And it actually does move forward. And on this part of the discussion, I'm going to, at first you will need to be using your imagination, but I'm going to have my friend with me. He's a good guy. He's smart and clever and helpful, and I like having him around. But he isn't scientifically trained in the sense that he observes carefully wipes out his already present conceptions, is available to do a consideration of non-intuitive stuff and tries to get an explanation based on what's actually happening. My opinion of that non-scientific way of existing and thinking is okay with me. I mean, I don't think there's anything wrong with being like that. And he has shown up, and we're talking, and I said, okay, we got a table. It's pretty stable. You can put your hands on the table. He said, okay. I said, now push down on the table where you got almost all of your weight on your hands and arms, and maybe 10 pounds of weight on your feet. And he says, okay. I said, all right, you can stop doing that. So we have a nice, stable, sturdy table that won't turn over. And I have a bathroom scales, and I want you to put them there next to the table. Stand on the bathroom scales. Put your fingertips on the table. Don't put much of your weight on your fingertips. To which he says, okay. And I said, and how much do you weigh? And he said, well, let me think. I got to remember the last time. And I said, no. Look down at the scales and tell me, do you see how much you weigh? They're on the scales. And he said, yes, I can see that. I said, all right, that's good enough. Now, here's something interesting. You got your feet on the scales. They're 8 to 10 inches apart. It's nice, balanced, symmetrical, stable weight in between your 2 feet. Each foot's holding up about the same amount of weight. And he says, okay. And I said, all right, and what I want you to do is keep your fingertips on the table for stability, but don't put much weight on your fingertips. I want you to take your right foot and lift it about a ½ inch off the scales. So your right foot is actually not supporting any weight. And he says, got it. And I said, so there you go. Now, and what your weight? What happened there? And he said, he said, no, my weight hadn't done anything. I said, no, I don't want to know what you think your weight is. Look down at the scales. And he says, all right, I did. Your right foot's off the scales, not on, it's up in the air, ½ inch. Yes, it is. What's your weight? It's unchanged. And I said, and that's what we thought would happen. And he said, yeah. I said, that's because the scales themselves are kind of cross-supported, cross-beam stabilized so that they don't much care where the weight is on them. They're measuring the weight. So if it's just your left foot sort of over to the left side of the scale, it's still going to give you your weight, even though your right foot's not there anymore. To which he says, okay. And I said, now when you lifted your right foot up like that, did anything move? And he says, huh? I said, your body, did anything move? And his reply is, no. And I thought, well, now, are you sure? And he's like, oh, well, my foot, I did. I lifted up my right foot. It's up in the air by ½ inch. And I said, okay, that's true. And I want you to think, of course, our understanding is you lifted your right foot up, nothing moved other than your right foot went up in the air a little bit. Yes, that's right. And I said, well, we're going to explore that some because your body may have changed and the weight distribution may have changed. I want you to consider, for example, your belly button. Where is that? You got your belly button? He said, my belly, what now? My belly button? I have my belly button. It's with me all the time. I said, well, where is your belly button? He says, it's on my stomach. And I'm like, well, anatomically, the human stomach is on the left side of the body, just under the edge of the rib cage. So that's not where your belly button is. Medically, your belly button is on your abdomen in the midline of your body, down there, near to your pelvis, right above your belt buckle. To which he said, fine, that's my belly button. I said, well, how about your belly button with respect to your feet? He's like, well, my belly button is way up in the air with respect to my feet. And I thought, yes, you're right, that's true. But let's take what we call the belly button line. And the belly button line starts at your belly button and goes vertically right straight down. And how does it come to be compared to your feet? And he said, well, it comes off of my belly button and goes down there and runs into the scales in between my feet. I'm like, that's true. But how is it related to your feet? And he says, it's on the scales and my feet are on the scales. And I'm like, okay, well, let's take a line that we're going to draw that goes from the instep of your right foot over to the instep of your left foot, a line that goes from left to right, and we'll look at the belly button line. And he says, the belly button line is on that line between my feet. I'm like, and what is this relationship? And he says, it's on it. And I said, no, let's get specific. For example, the distance between the belly button line and the left instep and the belly button line and the right instep, when you're standing there with both feet on the ground, nice balanced stance, what is that distance? And he says, I don't know. I said, look down at your feet. He goes, oh. He says, it's halfway. The distance from the belly button line to my right instep of my foot is the same as the distance to the left instep of my foot. And at this point, Our Lady picked up her instep and moved it against the clock and slid the clock across the floor at me. And I thought, you're messing up my train of thought here. And I went, oh, I'm out of time. All right, well, we'll stop. We'll give him a break, and we'll come back and make another lecture. All right, and again, hello, everybody, and welcome. We are continuing our discussion of a human mimicking robot walking along. And my thought process that one way to do this is to move the robot through a series of stances, because that allows you to actually create how you're going to get this to work. Because with this particular robot, it consists of a series of hydraulic cylinders for each leg. There's actually ones for the arms too. These were drawn when the robot didn't have arms. And if you wanted to completely describe the condition of this leg, for instance, all you would have to do is say, what is the amount of extension or retraction of this hydraulic cylinder, and this one, and this one, and this one, and this one, and this one. But, and for internal and external rotation of the leg, there's also a hydraulic cylinder in here. This hydraulic cylinder rotates the leg, internal and external rotation. But all you really need to do to describe the condition of this robot is have the amount of extension and retraction of each hydraulic cylinder per unit of time. And so it converts a hydraulic cylinder robot with people who are saying, how are you going to get this to work? You could actually make a listing of extension and retraction for each cylinder. So that's why I wanted to put the stances in there, because the stances describe, you can go to the stances and measure the extension and retraction and create a specification of each stance. And then with respect to time, you just move from one stance to the next one. I'll get into that in much more detail. Right now, we're at an upper level. And one of the things I wanted to talk about was counterintuitive. I think counterintuitive has two parts. The first part is you understand it. It's clear in your head. You've thought about it and seen examples, and you've seen it work. You know how it works and have an understanding. And the only problem with how you are understanding and seeing this is actually you're wrong. It doesn't work that way. That's the first part of counterintuitive. The second part of counterintuitive, someone who actually knows how it actually works, the first 2 or 3 times they explain it to you, your reaction is, well, that's not true. And a lot of, I think, this human mimicking robot issue has some counterintuitive features to it, particularly when they want to take capabilities of the robot and just not have them there because their equipment can't do this. And they convince themselves that that's okay because humans might have this, but it doesn't matter. When actually what's going on with human beings is a little bit counterintuitive. I think everything that human beings can do when they walk are important. And that's what we're working on. And we had our friend over here that was helping us with this. And as you can recall, I had my friend, he was standing on the scales, and we went through the belly button line, which is a vertical line coming off of his belly button, going straight down. And we asked him about it. He noticed that it came down and intersected the line going from one foot to the other foot about halfway. And then I asked him if he would just to lift his right foot about a half inch off the ground and to tell me what's going on with the belly button line. And he said, well, no, we've already done this. The belly button line goes straight down and it lands on a point halfway between the left foot and the right foot. I said, well, now you've got your right foot up in the air about a half an inch. Yes. And I said, well, I didn't really ask you to tell me how you understood it. What I wanted was look down there at the belly button line and tell me what you see. And he says, all right, well, I think we've already done this. He looks down and says, oh, gosh. And I went, well, and what's going on here? He said, well, it's moved over. The belly button line, it's coming down. It's almost touching the inside of my left foot. And I said, well, isn't that interesting? And I said, now your belly button is in your abdomen. Is your abdomen okay? It didn't get stretched or twisted or anything, did it? And he says, no. I said, well, how did the belly button line get over there like that? It moved to the left. And he thought, I think my whole abdomen moved to the left. And I thought, well, now, in human beings, you know, they're long, tall, vertical objects. Above your belly button is your thorax and chest, and below it is your pelvis. Anything get stretched or pulled there? And he said, no, I don't think so. And I said, so what does this mean then? And he said, well, this is so interesting. He said, when I was standing there even and balanced, the belly button line was in between my 2 feet. But now that I've lifted 1 foot off the ground by a half an inch, the belly button line has moved right over almost next to my left foot. And so has my pelvis. And so has my thorax and abdomen and shoulders. And I'm like, that's pretty interesting, isn't it? He said, yeah. Now, of course, it moved over there. What about your left foot? Did it do anything? And he said, well, no, of course not, because my left foot, I have all my weight on my left foot. It's locked down onto the scales, so nothing happened to it. And left leg, same deal. My left leg is connected to my left foot. My left foot can't move, so my left leg didn't move. And I said, all right, well, we're going to explore that a little bit. And before we go exploring, we'll take a look at this. I think it's always kind of fun to see what Microsoft has for us. This is the Bing desktop. I just upgraded to, and we will see, this is Tasman's Arch in Tasmania. And that's way above this water down here. Now, you know, I like to think here is what people are thinking. Here is math, science, and logic. Over here is what I'm trying to describe. It could be the robot people say, here is what is out there. Here is us bridging it into something that works. And here is where Dr. Gray is going to fall down into, because Dr. Gray is just wrong. I'm hoping I'm not wrong. I think I'm building a bridge. This is what allows counterintuitive to be taken away and put outwards and said, we're not going to do counterintuitive. We're going to do reality. That's my hope anyway. So back to reality. And here we can see with the robot, about what's going on with my friend. His right foot's off the ground, his left foot's holding him up, and the belly button line for the robot is right here, and that's coming right down vertically almost to his left foot, and he has noticed that. And I asked him, did you move your left foot? And he said no. And we want to talk about abduction, adduction of the leg. I think I'll do it in SketchUp because it's a little easier. This is that same drawing in SketchUp. And we'll take, okay, you can see here the right foot's off the ground, the left foot's holding up the robot. I put a little vertical post here to get a vertical line. And you can see that vertical line is coming off of the foot and going right up through the pelvis. And it's because the leg, the foot is not directly, see, if you put a vertical on the hip, the foot is not directly under the hip anymore. The foot is over on the inside, and that is abduction, adduction of the leg. And we'll take a look at that. And we're looking at 13A, so we will make 12 and 11 and 10 and 9, so you can't see them. And we want to look at what is abduction, adduction of the leg. And in the drawing that I made, here is that whole robot, and here is the right leg. And we've selected the entire right leg. Okay, we have the entire right leg selected, except we don't have the piston that controls it. And you can see that the right leg, there's a shaft through here, has a single place where it can rotate based on this hydraulic cylinder. And so if we put the rotation controller in there, lining it up on this, and come back out, we can see that the leg can move away from the midline, or it can move toward the midline, or until it runs into the left foot. But that's away from the midline is abduction of the leg, and toward the midline is adduction of the leg. So you can have abduction and adduction of the leg, which happened when this person lifted his right leg off the ground. There was abduction and adduction of his left leg to bring his body and pelvis over his left leg. He just didn't notice that. And I wanted to tell him, now remember when you're standing there nice and balanced and you look down with both feet on the scales, that your feet were about 12 inches apart. And now that you've lifted up your right foot a half inch in the air, where is your right foot compared to your left? And he says, they're 12 inches apart. And I said, no, one more time. Look down. And he says, all right. And he looks down and goes, whoa, my left foot is about an inch away from my right foot. And I said, you'll notice with your right foot and your right hip, your right foot is still under your right hip. But if you did the left hip line, which starts at the outside edge of your left hip and goes straight down, when you were standing there balanced, it went right down to your foot. But if you look at that line right now, that line has moved way over to the left. And what is going on is you have changed the angle of your leg. So let's let you stand on your right foot and lift your left foot up. And you can move your left foot away from your right foot. And he went, yep. And I said, move it out there about 12 or 14 inches. And you can move your left foot towards your right foot until it's almost an inch away. And he goes, yep. And I said, and now we'll go back. We'll put your feet square and symmetrical and then lift your right foot up. And you'll notice that your right foot is about an inch away from your left foot. And I'll ask you again, did your left foot move? And he says, well, no, it can't move. It's on the scales. And I said, well, this is one of these counterintuitive things where nothing is quite the way you think. And as I was doing that, she had been mimicking it and now was standing on one foot and pointing with her toe at the clock, giving me the message, amount of time. And I have a little bit more to discuss about this, so we'll start another video.